All right, well, welcome back after your too short of a holiday. And I've got some a syllabus for you here. Yeah, it does have a different title. It's Discrete Structures as opposed to Formal Methods. But it's Math 221 instead of Math 220. But but you know, the drill is the same. It's the same homework assignments, the same web page, only put a bookmark 221 instead of just change the 0 to a 1 and you'll be bookmarked. And not only that, sports fans, but the handout packet is twice as long.
We're still using all the old stuff.
Well, yeah. So this is the Old Testament plus the New Testament. All right. Now let me see if there's anything that I should I should go over that's that much different from what was before. And you know, it's all the same kind of stuff. I'll let you read the syllabus. There's some notices in there.
You have to sign it and return it to you?
And no, that's quite all right. But the syllabus will be on the first exam.
All right.
Just kidding. I actually heard one person, a colleague, say that he has a syllabus quiz to make sure his students read the syllabus. I don't think I'll do that. You did that nice, go. Yeah.
Credit for a day late.
Okay, now, so are there any questions before we get started? I hope we can keep this room. We had a little bit of a room mix-up here earlier. But any questions about the course? We're basically going to continue where we left off. In fact, do you remember where we left off?
Mathematical induction.
Yes, we left off. And
Wild guess.
And there was a wild guess because here we have mathematical induction. In fact, as a matter of fact, let's take a look at this. Let's take a look at this, this axiom and these two theorems that we had for mathematical induction. So if you recall, 12.3 was our axiom, mathematical induction over n. What is n?
Anything.
No, natural numbers. And which numbers are the natural numbers?
Counting numbers are 1,
0, 0, 1, 2, 3, 4, ... Those are the natural numbers. So that n with the extra bar in the middle is a symbol for the natural number type. And the axiom says that for all n, which is a natural number, if it's an if-then, right, in the body, it's if it's true that for all I, for 0 less than or equal to I less than n, and that p dot I is true. In other words, if it's the case that p dot I is true for all the i's up to, but not including n, if the truth of those implies the truth of the next one, of the n of p dot n. Are you with me? In other words, if you can show that p dot I is true for all I up to but not including n, if you can show that if that's true, then p dot n is true, then what have you shown? Now then what have you shown? That for all n what? P dot n is true for all n. Now this is really pretty slick, right? Because what do we have on the right-hand side of this axiom? We have on the right-hand side of this axiom that something is true for an infinite number, right? So there's an infinity involved here on the right-hand side. Are you with me? There is an infinity of truths. But what about on the left-hand side? Is there an infinity of truths on the left-hand side? No. There's just, if you can show that in general that p dot I is true for up to but not including n, if you can show that that implies that it's true for the nth one, that's just one proof. Are you with me? Then you have shown it for an infinite number. And then we proved, I don't know if you remember these details, you can actually, now that it's all recorded on video, you could go back and see that we proved 12.4 and 12.5 in class. That was some theoretical stuff that we did. And we wound up with 12.5, which is our working equation. Now, do you remember what our working equation is? What is this P dot 0? What did we call this P dot 0? That's the base case. Remember that? And what this says is that if you can prove the base case, P dot 0, and then if you can show that if P dot I is true for up to and including n, if that implies that it's true for the n plus first one. And what case was that? What did we call that case?
Induction.
That was the induction case. Yeah. So if you can show the base case and the induction case, then you have proved that P dot n is true for an infinite number, for all n. Right? And so this 12.5 was our working equation, and we did an example, you did a homework problem, and then we actually had a question like this on the final, if you remember. So I think what we should do now is do a couple more examples of proof by mathematical induction, and you'll have some homework problems for that as well. Okay. So let's prove, let me see, what should we prove? Let's prove, let's prove 12.4c. Let's prove that the sum on I, 0 less than or equal to I less than n of, this is body of 2 to the I equals 2 to the n minus 1 for n is greater than or equal to 0. Now, actually, before we prove this, you want to do a little example? Maybe let's see, because what is this? This is, what are the values of I? Let's do this. Let's before we prove this, let's just do an example. Let's do an example with n equals 3, okay? So with n equals 3, what is this saying? What are the possible values of I if n is 3? 0, 1, and 2. So this would be 2 to the 0, 2 to the 1, 2 to the 2. Are you with me? And what is this operation? Addition. So it's 2 to the 0 plus 2 to the 1 plus 2 to the 2, right? And we said if n is 3, we are claiming that this is what? 2 to the 3 minus 1. We are claiming that this is 2 to the 3 minus 1. Well, what's 2 to the 0? It's 1 plus 2 plus 4, and we're claiming that this is 8 minus 1. Well, 1 plus 2 is 3 plus 4 is 7. 8 minus 1, son of a gun.
Amazing.
Did we just prove it?
No.
Proof by example. Unfortunately, we did not just prove it.
Well, if you put an infinite number of examples,
Well, right, but see, and that's the whole thing about proof by mathematical induction is we don't have enough time or space to do an infinite number. So that's our example of how it works, but now let's prove it. Now, so what do we write down first?
base case.
Base. So what must we prove?
It's true for 0.
Yeah, so we start with this, right? We write down the whole thing. Yeah? Remember that? Okay, so we do sum on I, 0 less than or equal to I less than n, 2 to the I equals 2 to the n minus 1. And then we say equals by the base case. Oh, and we have to say what the base case is. Now, how do we identify the base case? How do we know what the base case is? It says for n greater than or equal to 0. So this tells us what the base case is, right? So the base case is here 0. Okay, so then we just plug in n equals 0 here, right? So sum on I, 0 less than or equal to I less than 0, 2 to the I equals 2 to the 0 minus 1. Right?
Right.
Math, good. Equals by math. Now, what are the possible values of I here? 0 is less than or equal to I, is less than 0.
Is I
So-
still a natural number?
Yes.
Okay.
Well, no, it could be integer, actually.
But it can't be a fraction.
Can't be a fraction, yeah.
Regardless, it's false.
But regardless, this is false. So by math, this is the sum on I of false.
Empty range.
2 to the I equals 2 to the 0 minus 1. And false, yeah, good call. Did everybody hear that? What do we know about false? Empty range rule. Now, where was that?
The very first axiom of
Man, we've done a... Oh, no, I'm going the wrong way. I was going up instead of down. Empty range, 8.13, empty range. So this equals by 8.13, empty range. Yeah, and it equals u. Oh, but what does u mean? That's the identity. Empty range and the identity of what operation?
addition.
Okay, identity of sigma, or of addition, let's say plus, is 0, right? So this whole thing is 0 equals 2 to the 0 minus 1. And now we can do more math. And we get what?
0.
0 equals 0.
Base case.
That's done. Yeah? And that's usually the easier part.
Now we write something.
Now we have to write something. And remember, I'm real sticky about making you write this sentence. So do you remember how that sentence works?
Something about inductive case.
Must prove. Yeah, okay, so first we write inductive case.
Something about hypothesis.
And something about the inductive hypothesis, right. So what do we show? What do we have to...
Did you have to say prove that with the end plus one?
Yeah, we have to prove, what we have to do is we have to prove that this is true when n equals n plus 1,
By using the inductive method.
assuming, yeah, right, assuming that this is true for just n, right? So you have to write that all out. So we have to say must prove, or we'll just say prove,
Wrong.
prove, sum on I, 0 less than or equal to I less than n plus 1, body 2 to the I equals what? 2 to the n plus 1, and then minus 1, right?
By using the inductive hypothesis.
Yeah, assuming. And then you have to write it all out again. Sum on I, 0 less than or equal to I less than n, 2 to the I equals 2 to the n minus 1. And then you have to identify it as the inductive hypothesis. And remember, because remember what we're doing is what are we, let's see.
Why are we allowed to assume that it's true for n?
Yeah, that's a good question. Why is it, do you remember how that works? Because basically what we're trying to prove is that this implies this. See, here's what we're doing. Here, let me just write it all out over here. What we're doing is this. We're proving that here. We're proving that the sum on I range 0 less than or equal to I less than n body 2 to the I equals 2 to the n minus 1. This whole thing implies
And we're allowed to assume context.
and that's the technique that we use. Sum on I 0 less than or equal to I less 0 less than or equal to I less than n plus 1 body 2 to the I equals 2 to the, oh, this was wrong. This is 2 to the n. The minus 1's down here. 2 to the n plus 1 minus 1. Actually, what we're doing is this. But we always use the technique of assuming the conjuncts of the antecedent. Are you with me? And that's why this, that's what this is. We're doing this implies this. Only difference is with 12.5, it's not, see, here's the thing. With 12.5, it's saying not only this one, but the one that went before that and the one that went before that. So there's actually a lot more conjuncts here, and we're only assuming just one of them. Are you with me? Now there's going to come a point where we're going to have some problems where we have to go to this one and the one before, and that's the way it is in general. All right. So anyway, so this is so here's the proof. So the proof of the induction case is now, what is it now? Which one of these are we trying to prove? It's this one, right?
First one.
Now, should we start with this because this is an equals? Should we start with this and get it equal to this, or should we start with this and get it equal to this? What do you think?
The left. Start with the whole thing.
No, don't start with the whole thing. Don't start with the whole thing. Start with the left, and then use what technique? Split off term technique, yeah. So we'll start with this, right? So it's sum on I 0 less than or equal to I less than n plus 1 body 2 to the I equals by split off term.
We're splitting off the first term or the second last.
Good question. Which term should we split off? Because what do we want to do in our proof here? We want to use what? One of these steps here, what are we going to do? We're going to use this.
So take off the last.
So take off the last one. Okay, so this is by split off. Okay, so who can split off this term? What are the possible values of I here? 0, 1, 2, 3, up to, and what's the last one? Is it n or is it n plus 1? It is n. So this is what? So how do we split off? Sum on I. This time it's less than n because we're going to split off the term. Body 2 to the I, and then and now what's the operation? Plus. And the last one that got split off was 2 to the n. Is everybody clear on that? Plus 2 to the n.
Then you do inductive cases.
And then this equals by the inductive hypothesis. Because now we know by the inductive hypothesis that this equals what?
2n minus 1.
So we have 2 to the n minus 1 plus 2 to the n. Now, what are we trying to get this, what are we trying to prove? See, the nice thing about writing this down is you can see what you're trying to get to here. We're trying to get it to this. So this equals, by math, well, what's 2 to the n plus 2 to the n? 2 times 2 to the n, right? So this is 2 times 2 to the n minus 1. But what's 2 times 2 to the n? That's 2 to the 1 times 2 to the n. So that's 2 to the what? 2 to the n plus 1. Is everybody good on your algebra here? So this equals, by more math, 2 to the n plus 1 minus 1, and boom, we're done.
Who'd have thought that mathematical induction uses so much math?
Or induction.
Or induction.
Okay, is everybody good on this? Let's do another real quick one before we move on to some more complicated ones. Let's do, well, this is so similar. Well, but, okay, here, let's prove this one. Let's do this one real quick. We can do this one pretty quickly. Let's do, my sigma is still not very, yeah, I'm trying to get my sigmas to look right.
Okay, 5.
Okay, so let's do sum on I, 0 less than or equal to I, less than n. This time let's do 3 to the I. And guess what this is? This is 3 to the n minus 1 divided by 2.
What?
For n greater than or equal to 0. Okay, so we won't bother with an example. So let's do the base case. So what do we have to, what is it on the base case?
Same thing.
0 less than or equal to I less than n. 3 to the I equals 3 to the n minus 1 divided by 2. So equals, by the what? Base case, n equals 0. And so this is going to be sum on I, 0 less than or equal to I less than 0. 3 to the I equals 3 to the 0 minus 1 over 2. And this equals, by the, now let's just, let's do 2 steps in one. 0 less than or equal to I less than 0 equivalents false
Empty range.
and empty range. So this will be what? 0 equals 3 to the 0 minus 1 over 2. But 3 to the 0 is what? 1. 1 minus 1 is? 0 divided by 2 is? 0. 0 equals 0 is?
True.
So equals, by math, 0 equals 0. Boom, we're done. Yeah? But now what about the inductive case?
Prove n plus 1.
Yeah, must prove. So prove sum on I, 0 less than or equal to I less than n plus 1 body 3 to the I equals what?
3 to the n plus 1.
2 to the n minus 1 over 2.
3 to the
N plus 1 minus
n plus 1 minus 1. No,
Minus 1.
n plus 1. Is the minus 1 down here?
Yeah.
Minus 1
over 2.
over 2, assuming sum on I, 0 less than or equal to I less than
And
n, 3 to the I equals 3 to the n minus 1 over 2 as the Okay. Man, I'm running out of ink here. I have to go get a new pen. Wonder if this is very full. Yeah. That's also kind of weak. Okay. Now,
Start with the left side.
start with the left side. Sum on I, 0 less than or equal to I less than n plus 1, 3 to the I equals, and what's always the first thing that we do? And we're split off term. So this is, let me see, this, what's the last value of I here? N. So this will be sum on I, 0 less than or equal to I less than n, body 3 to the I. And what's the operation? Plus, because of the sigma.
3 to the n.
And the last one was n, so 3 to the I, it makes that 3 to the n. Is everybody good? And this equals by inductive hypothesis. 3 to the, yeah, this is 3 to the n minus 1 over 2 plus 3 to the n. Now, how do we do this?
2 3 to the n.
We need a common denominator, right? Equals common denominator. Common denominator. So this is 3 to the n minus 1 plus 2 times 3 to the n over 2. Is that right? Oops. Oops. Are we good?
More math.
So equals by math. Okay, I'll let you fill out your notes. Equals by math. So equals by math what? So in your notes what it will be? So it was 3 to the n plus 2 times 3 to the n.
It's 3 to the
That's 3 times 3 to the n. And,
which is 3 to the n.
and then 3 times 3 to the n
Is 3 to the n plus 1.
is 3 to the n plus 1. And then we'll have it. Yeah? Oh, that was too simple. That was too much like the previous one. Okay. Now, so these ones proving summations are all very straightforward. They kind of follow the same recipe. But now the next one that we're going to do is a little bit trickier because you can prove not just equalities, but you can use proof by mathematical induction in many different situations. One of which is not just equalities, but inequalities. Okay? Now with inequalities, it's a little bit trickier because you have to use reasoning. I mean, you have to reason about inequalities that maybe you're not used to reasoning. I mean, reasoning with equalities is one thing, but reasoning with inequalities, it's a little bit trickier. You have a little bit more flexibility with inequalities, and you have to be a little bit more creative sometimes in your proofs. All right? So here's how, so let's do an inequality. So here we go. Proving inequalities. So let's prove this equality. Let's prove that 2n plus 1 is less than 2 to the n for n greater than or equal to 3. Do you believe this? By the way, what happens if, let's just try it for 1, for n equals 1. If it was n equals 1, what's 2 times 1 plus 1? What's 2 times 1 plus 1? 3. And what's 2 to the 1? 2. So, yeah. So it doesn't work for n equals 1. It also wouldn't work for n equals 2. But if n equals 3, what's 2 times 3 plus 1? 7 is less than,
8, 6, 8.
what is it? 8.
I did multiplication.
Yeah, so when it's 3, 7 is less than, oh, we just did the base case actually. Okay, and for 4 and 5 and 6, but we want to prove it in general.
Right.
See? Okay, so base case, yeah, actually we just did the base case verbally, so let's write it down. So base case. Base case. So what do we write down? We write down the whole thing, right? 2 to the n plus 1 is less than 2 to the n equals, by the base case, what?
Equals 3.
Oh, base case, yeah, we have to say what n is. And
You
up
have to do that, right?
yeah, base case n equals 3. You have to identify what the base case is. Yeah. So we plug in, so this is 2 times 3 plus 1 is less than 2 to the 3, and this equals by math.
7 is less than 8.
7 is less than 8, and boom. Is everybody good with this? Now, but what about the induction case?
What about it? Prove n plus 1.
Yeah, so now what do we have to prove? So must prove that what?
2 times n plus 1 plus 1.
Prove that 2, and here it's going to have to be 2 parentheses, n plus 1, right? Plus 1, yeah, that's this plus 1, yeah, is less than what?
2 to the n plus
2 to the n plus 1,
1.
assuming
2n plus 1.
2n plus 1
2 to the n.
is what?
Less than 2 to the n.
Less than 2 to the n as the inductive hypothesis.
Can't do the equals thing this time.
Well, we can't do the equals thing, but we can do the less than, we can do the greater than thing.
Oh, that's it.
See, now watch how this works. I feel like getting a new pen.
You use green or blue.
I wonder if one of those, I know those colors don't show up very well in the video. Is that pretty dark? Did you find a dark one?
Blue's working.
That's pretty good. This one might
It's
work.
fine, just the green isn't.
Okay. Okay. So now check this out. Oh, we did the base case, right? So now look, what is it that we have to prove?
2n plus 1.
That this is less than this.
Can we start with one side?
Yeah, we can start with one side. Now the question is, which side do you want to start with?
The left.
I wouldn't.
Oh.
The other one is, because look, you guys, if we start with this one, if we start with this side, we can kind of like, sort of like, split off a term here. Do you see what I mean?
Fine.
You can technically do that with the other side too.
Well, yeah, but I think it would be harder. So let's start with the right side and get it to be what?
Greater than.
Greater than the left side. Are you with me? Okay, so 2 to the n plus 1. So we start with 2 to the n plus 1.
Start with little math.
Yay.
And we start with a little math.
2 times 2.
This equals,
Oh.
by math, yeah, what is this equal to by math? 2 times 2 to the n. Right?
I'm not very good about
Well, you got to, this you need to do, you better brush up then.
because I thought that was 4 to the n.
No.
Danger. There it is.
Oh, no. See, it's not, the parentheses, the exponential has higher precedence than the multiply.
Sure. Okay.
Are you, is that, yeah, if we had a paren around here, it would be 4 to the n.
Okay, so we do this greater than the
Yes,
hypothesis.
and this is greater than, very good call,
What?
by the inductive hypothesis.
2 times 2 to the
Because look, what do we know by the inductive hypothesis? By the inductive hypothesis, we know that 2 to the n is greater than 2n plus 1, right?
Okay.
So the-
See? And so therefore, 2 times, now here's where you have to use some math reasoning.
If 2 to the n.
If 2 to the n is greater than 2 times n, then 2 times 2 to the n is greater than 2 times.
2 to the n, or 2n.
Is everybody clear on that?
Okay, fine.
So if 2 to the n, okay, so this is greater than what? So this is greater than 2 times what?
2n plus 1.
2n plus 1.
2n plus 1, right? Because if you see what we're saying is that if 2 to the n is greater than 2n plus 1, then 2 times 2 to the n is greater than 2 times 2 to the n. But everybody, do you buy that? That's some reasoning with inequalities, right? Okay, but this equals by math what?
4n plus 2. It's off a little. Oh, it has to be less than.
Ah, see, and it is off a little bit. It is off a little bit. But now look, watch this. What are we trying to prove? We're trying to prove that this is greater than this, right?
Right.
So what we have to do is we have to get that into a form that has this plus some stuff left over.
We can do.
So let's write this down.
Write it down.
Well, I mean, see, let's write down this equals by some more math. Here, watch this. Yeah, this is kind of tricky. This manipulation is a little tricky. What are we trying to get this to? 2 times n plus 1 plus 1, right?
Yeah.
So it's 2 times n plus 1 plus 1. That's what we're trying to get it to. But this, at this point, for sure does not equal this,
Bigger.
right? So it's plus, but how far off are we? Are we off by a plus or a minus or what? I mean, what, how could,
Plus 2n minus 1.
because what do we have here so far? We have 2n plus
2n plus 2.
plus 3. What do we have here? 2n plus 3, right?
Yeah. No, we're at
Yeah, so
4.
we're off by 2n minus 1. If you're adding.
That's 2n minus 1.
So is this plus 2n minus 1?
So-
Yes, so. Yeah,
Is that right?
That is it. Yes.
Now how do we reason?
No, if we do math, that'll just get us.
Well, what?
4n.
Well, I mean, we know that this equals this, but what are we trying to, what's the whole thing that we're trying to prove? That this is what?
We can take that.
This equals this is greater than this equals this equals this. If I have something greater, if I do another greater than,
Oh, okay. 2 times n plus 1 plus 1.
but is that true? I mean, how do you, but
Because it's greater than 3.
2,
The n has
and what we're saying, this is 2 is n plus, we're saying that this is greater, we are claiming that this is greater than this.
Yes.
But why is that greater than
Because
this?
2n is greater than 1 at all times.
Because 2n minus 1 is what?
Positive.
But for which values of n?
N greater than 3.
Yes. Because 2n minus 1 is greater than 0. It's positive. Are you with me?
Yes.
Because this is plus a positive number. We are because this for n greater than or equal to 3, because that's n greater than or equal to 3 is what we were trying to prove it for, right? And then boom, we're done. Now, you guys, this is a little tricky, especially this here, here. But notice that it depends on transitivity. If A equals B and B is greater than C, then what?
Then A is greater.
A is greater than C. If C equals D and D equals E and E is greater than F, then what? D is what?
D is greater than
Greater than F. So if A is greater than D and D is greater than F, then what?
A is greater
A is greater than F. I mean, we're using transitivity, this whole sequence of things. As long as but you can't, if you have a greater than on one step, you can't have a less than on another step. Then transitivity doesn't work. Are we good? All right. See you tomorrow. I hope in this room. I'm going to have to...